Good morning, everyone. Thank you so much for joining us our live stream today. I think we can start now. Thank you so for joining. My name is Anya, and I'm a business development manager of K-Mine. Before we begin, I would just like to remind everyone to follow our LinkedIn page where we post announcements for future streams. So today we're going to be talking about a very important topic for mining companies, especially that are in development and production. We'll be discussing the impact of pit wall stability on mining economics. Now, as you all know, pit stability is a critical factor that directly affects mining operations, safety, and profitability. Without the proper management, mining companies can face high cost, lost production, and have accidents also. So if you're looking to improve your mining operations, reduce cost, and ensure the safety of your workers, this is webinar for you. Let me give you a short overview of what we, as a software company that specializes on mining industry specifically, offer in general, besides the functionality we will discuss further. We have been on the market for almost 30 years and provide one standalone application that is customizable and adaptable for each company's needs. Our solution is model-based, and it allows us to work with companies of any size and provide reasonable prices as well. Our application is based on our patent graphic core, which processes information faster, and we aim to cover most of operational needs, such as 3D modeling, resource estimation, and planning. Today, we have built 12 models for companies that are in exploration, development, or production stages. Each of these models can be configured, adjusted, and enhanced for each deposit and for open pit or underground mining as well. Also, each of these 12 models can be used as a standalone model or in conjunction with each other. That allows different departments of a company exchange information within one space without the need to create SharePoints, fight compatibility issues, or waste time on import or export processes and adjustment of the data. And we also offer custom solutions and end-to-end planning to automate production stages. So at K-Mine, we understand the uniqueness of each mining project. That's why we offer additional services to mining companies that are in exploration, development, and production stages. With a team of mining engineers, geologists, planners, surveyors, and other professionals, we provide services such as resource modeling, mining engineering, and audit. Our engineers not only set up the whole company's infrastructure during the implementation of our solution, but also assist our clients at any stage of work, creating 3D models, planning schedules, and estimating resources and reserves. So if you're interested in any of the services or any of these models, please reach out to us, drop us a note, and we'll be happy to discuss it with you in more detail. So today we'll cover the importance of calculating pit wall stability indicators in mining operations. We will discuss the method of calculation and features of K-Mine stability analysis model, and we will present a use case to demonstrate how the stability analysis calculation is performed and how the optimal resulting slope angles of pit wall are found. And then we discuss the evaluation of the influence on ultimate economic measures and finish the webinar analyzing the evaluation of the results. So when mining companies use an open method, it's super important to make sure that the rocks don't collapse at the edges and the sides of the pit. Basically, the angle of the slope is what determines how stable it is. If the slope angle is too steep in the construction plan, it can lead to a sudden collapse of the pit walls or ledges. But if the angle is too low and the pit is really deep, then it can be too expensive to mine. For example, in a pit that is up to 300 meters deep, decreasing the wall inclination angle just by a few degrees can increase the volume of overburden by millions of cubic meters per kilometer of work. So geomechanics have to figure out how to balance rock safety with productivity. And they use the same methods and tools as they do for underground mines. So basically, the stress of the soil is what makes up the slope, depends on how heavy the rocks are and anything else like buildings or machines that are sitting on the side of the slope. When the slope gets steeper, the tangential stresses go up, and if they go too high and exceed the shear resistance limit of the rocks, then the slope goes out of balance and slides along the specific surface. So when the height of the ledge increases, we need to make sure the slope stays stable by reducing the angle of inclination. But the slope height and angle are affected by a bunch of natural factors like how strong the rocks are or how fractured and layered they are, and the orientation of cracks and layers in relation to the slope, and as well as other things like groundwater level and technological factors. That's why we need to do some geotechnical surveys to assess the stability of existing slopes and calculate laying angles for planned objects. Even though the rocks can be complex and hard to work with, we can still calculate the slope elements with minimal errors. So when we determine stability, the composition of rocks that make up the sides is what is the most important. If the rocks are homogeneous and possess constant physical and mechanical properties, we can use analytical dependencies to evaluate stability. However, if the sides of the pits are made up of layered rocks of varying thicknesses and orientation to the horizontal plane, and the atmospheric precipitation affects the physical and mechanical properties of the rock mass, along with the additional load from heavy mining and transport equipment, then the calculation models become much more complicated. In these scenarios, closed analytical dependencies are no longer applicable, and the researchers must turn to numerical or digital models to assess the stress-strain state of pits and dumps with various shapes and compositions. These numerical models allow us to evaluate pits and dumps composed of rocks with arbitrary structures and variable physical and mechanical properties. So as far as K-Mine software, our tasks allow our users to manage rock masses, helping them tackle complex issues such as calculating stability or deformation in open rocks. And geomechanics in general is a multidisciplinary field, as it includes mechanics of deformable medium, geology, hydrogeology, geotectonics, engineering geology, and seismic events impact. In mining geomechanics, we utilize various methods to determine the slope stability by computing the stability coefficient. One of the useful tools in identifying the sliding surface present within the structure is the theory of limit equilibrium, as it allows to ensure safe and stable mining operations. Holding and shearing forces also play a significant role in geomechanics, as we address them through the application of algebraic addition or polygonal forces techniques. And these methods enable us to deal with challenging rock mass management issues and maintain the stability of mining operations. We utilize various methods to determine the slope stability factor while also creating graphical representations of prisms that may collapse. To get started, we require some initial information such as physical, mechanical, and strength properties of the rocks in the area of interest, the structure of the ledges located at different elevations, and the calculation area boundary. This information serves as a foundation for our assessment, allowing us to evaluate the stability of the slopes accurately. With this critical information in hand, we can determine the risk of potential rock collapses and take necessary measures to ensure the safety of our operations. In order to determine the calculation area, we need to create two limiting lines that are perpendicular to the edges. These lines can be set using the polyline object, which you will see further in the demonstration. When constructing these lines, we need to make sure that they cross all of the edges along, which we need to perform calculation in the top view. Moving on to the stability calculation, there are several methods that are available to us. We can use the method that we want by selecting it from the method list. And the list includes methods such as method of algebraic addition of forces, calculation methods with foundation uplift, force polygon method, and force polygon method in heterogeneous medium. Depending on the method we choose, the appearance of calculate slope stability window may slightly vary. But once calculation is completed, the results will be displayed in the lower part of the calculation model window, which you will see further. And additionally, we will be able to view these results graphically in 3D. Okay, so let's talk about each of these methods in detail. The method of algebraic addition of forces involves graphically displaying prisms of possible collapse that help us determine whether a slope is safe or not. To use this method, we need to specify or select the physical and mechanical properties of the rocks, and then divide the calculated prisms of potential collapse into a number of smaller prisms. Additionally, we can utilize the filter that take into account seismicity by enabling the appropriate flag. In addition to the safety factor, we can also calculate the slope angle for a given stability factor. This information is incredibly valuable because it allows us to design and implement slope stabilization measures that are effective and efficient. So overall, algebraic addition of forces method is an essential tool in the field of slope stability analysis because it allows us and provides us with valuable insights into the slope stability as well as its ease of use, and it makes it crucial technique for anyone that is involved in mining projects. Next method is the calculation method with foundation uplift, and it's used to determine the stability of slopes in areas such as dump sites or tiers, taking into account holding and shear forces caused by foundation uplift and plantar deformation from a weak foundation of high power. The calculation of stability starts with the search of the most stressed sliding surface in the rock area. Then an iterative construction is carried out from the minimum possible sliding prisms and that are limited by the sliding surface approximated by 3 arcs of circles. To perform calculations using this method, we need to enter rock properties for the foundation and the upper layer separately by selecting the Set button in the corresponding calculation field. And then the calculation is performed using 2 selected polylines drawn along the normal to the analyzed slope. The result obtained while calculating slopes on a weak foundation covers only the slope from the first lower edge, which is basically the boundary of the rocks of the weak foundation by default, and to the last upper edge that intersects the calculated profiles represented by a polyline. This method is incredibly useful in accurately assessing the stability of slopes and ensuring the safety of individuals and equipment in this area. The next method is force polygon methods, and it's another way to calculate stability in a homogeneous area by taking into account shearing and holding forces through vector addition. Once you choose this method, you need to enter data about physical, mechanical, and strength properties of rocks, similar to algebraic addition of forces. Apart from typical stability calculation, this technique considers hydrostatic weighing under watered slope conditions for dispersed unbound rocks. To account for hydrostatic weighing in the calculations, we have to indicate the layer in which azohypses of the groundwater level are located in the upper boundary of the aquifer field. This method is very helpful in assessing the stability of various structures and ensuring the safety in mining projects. It's essential to use this method to avoid potential accidents and damages that occur due to unstable structures. And the next method is the force polygon methods in anisotropic medium, and it's a tool that is used to calculate the stability of a heterogeneous massif, which takes into account the shearing and holding forces by using the vector addition of forces. This method considers various properties of the rock that fall into the prism of possible collapse, and the search for the most stressed sliding surface is carried out by an iterative method. So what distinguishes this method from calculating stability in a homogeneous massif is that the rock properties needed for the calculation are automatically extracted from the block model, which is entered during its creation. Furthermore, taking into account seismic impact, water slope, and the presence of weakening surface is done in a similar way to the polygon of forces method in a homogeneous medium. The construction, output on information about calculation, and calculation of the inverse problem are performed similarly to the polygon force method in a homogeneous medium. And the last method is a task calculate FEM stability, which stands for finite element method. It's used to determine the stability factor and stress strain state of slopes, pit walls, and dumps. This command makes use of the finite element method, which is a numerical technique that involves dividing the area under analysis into a finite number of sub-areas or elements. This helps in carrying out an elastoplastic calculation. To determine the slope stability factor, we use the strength reduction method, which involves finding a stable solution to the problem while simultaneously reducing the strength characteristics of the rocks in the massif. So in order to begin the task of calculating FEM stability, it is necessary to construct a geological section using surface object with a double fill and build polylined objects to act as a boundary conditions. So now we can explore the geomechanics model in K-mine in more practical context. Our objective is to optimize the angle of inclination of pit wall to achieve an economic benefit. So to start, we'll determine the current stability coefficient and then proceed to optimize it. First of all, we make use of the initial design coordinates of conditional open pit, as well as the framework of the open pit and the rock formations that contain the mineral deposit. The stability calculation, which utilize FEM, is performed section by section. So this allows us to utilize the criterion section tasks to obtain a slope section that takes into account the mining location and the rock formations. We trim the superfluous portions of the sections and switch to the working view. And then we initiate the FEM stability calculation task. Subsequently, in the task menu, we should upload the rock list, define their characteristics, and establish the association between the surfaces on the section and the rocks mentioned in the list. Now let's talk about the limiting factors that we need to consider. Once we've taken those into account, the next step is to create a grid of a certain size, determine the number of iterations, and set the required accuracy. And after that, all we have to do is to hit apply button, which within a few seconds will have our results. So each result we get comes with its own stability map, which has its own legend and stability factor. So let's look at the results we obtained so far. To perform the task, we need to do it in two stages. First, for the stable rocks, and then for the weak overburden. Now let's perform a comparable calculation for the overburden. With some parameter reconfiguration, we can easily run the calculation again. The stability factor for the overburden is 1.79, indicating that this section is not extremely stable. While the coefficient is considered normal, there is no need to reduce it at this time. However, we can optimize the factor of 3.64 for the rock formations, which presents an opportunity for improvement. And to achieve this, we can utilize the calculate the slope stability task for our section. We'll pick the prism that connects the zeroth and sixth ledges from the result list. And then we'll input the required safety factor, like 2.7, in the required stability factor field and run the calculation. Using this approach, we arrived at a stability factor of 3.7, which closely matches the factor derived from the FEM method. So additionally, a prism that could potentially collapse has emerged on the section along with the slope angle of the pit wall that achieves a stability factor of 2.7. In our specific case, this angle is 42.3 degrees, and we can incorporate this angle into our design to observe any resulting differences in the outcome. In the process of optimizing the resulting pit slope, we need to pay close attention and make the final decisions only after we consider all the factors. It's crucial to have complete confidence in the incoming information and calculations to avoid any mistakes and risks associated with destabilization of the mountain range. Now let's move on to the topic at hand. We'll examine how the slight changes of the resulting pit angle can affect a small iron ore pit. We'll create different scenarios in the pit optimizer model to illustrate this. It's one of our other models, and it's essential to understand the significance of these changes and the potential impact on the outcome. Therefore, it's essential to approach this process with caution and care while taking all necessary steps to make informed decisions. We always have to understand the risks and potential benefits associated with the process of optimizing the pit slope. So in order to develop a project to search for optimal contours, we require a block model and the current mining position in the pit. However, to consider the present state of mining operations during the optimization process, we must restrict the block model to a wireframe before incorporating it into a project. To achieve this, we utilize the set property command and choose the appropriate geometric constraints. Now the block model is prepared and shown blocks correspond to the constrained surface. We can confirm this by exhibiting the surface as a wireframe or lines. To initiate the project creation process, access the optimal pin boundaries command and complete the primary fields. These fields include the project name and the location where it will be saved on the local computer. And to make the information more readable, we'll configure the display of calculation results to present values in millions and with a single decimal point. Additionally, we'll set up the wireframe settings while leaving the horizon settings unchanged, as they won't be necessary for today's example. So now we'll incorporate a restricted block model into the project. On the Properties tab, we'll indicate the fields that we'll use later on, such as quality indicators and material class attributes. For all other data, we fill them in manually. Afterward, let's input the specific weights for the block model rocks and include valuable components for each of the mineral types. We'll also create a subdirectory in the project tree and choose the relevant block model for further use. Keep in mind that although multiple block models can be utilized in the project, only one can be involved in the calculation at a time. And next, we'll configure the indicators for the resulting pit angles. For rocks, we'll use 39 degrees, and for soft rocks, we'll use 30 degrees. These angles can be defined by filling in two fields, the default field and the angle of inclination for soft rocks from the material class attribute. The next step is to determine the economic indicators. To conduct a more comprehensive analysis of the output data, we'll establish a price adjustment coefficient step of 0.02 within the range. This setup will enable us to observe all changes for analysis purposes. Let's assume that we're mining ore and we're mining iron ore, and we'll use it to produce a concentrate and then high quality direct reduction pellets, and each will be worth $150. To set the cost of enrichment, we'll use a value of $12 and the cutoff grade will be 12.5 and above. The last step is to input the recovery factors, which we'll set at 0.38 and 0.3 for high and low quality ore respectively. We proceed to the mining cost step and establish the excavation cost for each of the rock groups, empty rocks, ore, and soft waste. Since transportation costs aren't pertinent in our current analysis, we'll use a fixed value of $2 per ton. To compute NPV, we'll need to set the discount factor and annual productivity. So let's begin the calculation, which will take only a few seconds. And there we have it, the results are in. To make it easier to understand the data, let's navigate to the chart tab and change the data display mode to differential. From this, we can infer that there isn't a substantial increase in minerals after the 7th coefficient. Thus, we can select this price adjustment coefficient for comparison with future calculations. And let's create a similar scenario with a slight variation. This time we'll choose an angle of 42 degrees as the resulting angle of the pit for rocks and leave all other settings unchanged. To make a reliable comparison, it's essential to repeat all the scenario settings accurately. So we should aim to compare apples to apples and avoid matching several scenarios with variation in several data points. However, in some cases, changing several initial data points can also be useful for comparison. For example, if there is a change in production technology where all parameters associated with a final product change, such as the cost of the product, the cost of enrichment, and the yield of the final product, and so on. So once the calculation is finished, we'll review these results in the same manner as the previous scenario. However, the differential graph presents a slightly different pattern. For a specified pit wall inclination angle, a distinct coefficient will be optimal, and we will choose it as number 5, which is 0.68, and compare it with the coefficient of 0.72. In advance, we also can conclude that the increase in the angle has optimized the shell. This means that the same quantity of ore can be extracted with less overburden and with the same price adjustment factors, which is 0.72, we obtain more ore. However, we'll delve into numbers later. We'll export data from the resulting tables to Excel for a more comprehensive analysis. So let's create wireframes based on the scenario and coefficients we're interested in. We'll assign different colors to them to make things more clear. First, we'll use the color red for the wireframe that represents an angle of 39 degrees and coefficient of 0.72. Next, we'll use a color purple for the wireframe that represents an angle of 42 degrees and the coefficient of 0.68. And finally, we'll use the color blue for the wireframe that represents peak of 42 degrees and coefficient of 0.72. Assigning different colors to each wireframe will help us to distinguish them from one another and make it easier for us to analyze the results. So next we'll attempt to examine the distinctions between shells that we've obtained in the sections. To do that, we'll construct a section along the guideline and only exhibit the intersections of the wireframe and the guide. So let's take a closer look at the cross-section. Initial observation revealed that when the pit wall has the smallest inclination angle, a larger quantity of both soft and hard overburden is extracted, which is expected. For an inclination angle of 42 degrees, shells with coefficient 0.72 and 0.68 are nearly parallel. However, the shell with a coefficient of 0.72 is deeper throughout the gap, indicating that more rocks will be extracted, which is also logical. Nevertheless, the key issue remains with the numerical expression of these indicators. Even minor discrepancies over broad areas may result in the significant variations in volume. Consequently, choosing the optimal contour should be done carefully, taking into consideration all the factors that are relevant to the user. To answer to the question of which contour is the best to adopt can only be determined by the numbers. And let's dive into the numbers and see what they have to say. This is usually the stage where we get the most answers. First, we're going to compare the two options with an angle of 42 degrees to the initial option we accepted as the main one, which is 39 degrees and a price adjustment coefficient of 0.72. We're going to split the comparisons into two parts: economic indicators and indicators of the export of rock mass, which are directly related to each other. Let's start by looking at the export of rock mass. The option with the steeper slope angle removes 12 million tons more rock mass than the option with the angle of 39 degrees. The ore is also 3 million tons more, and the overburden is 9 million tons more. The stripping ratio for the increment in ore overburden is 3 tons per ton, which is not very attractive, and especially given that the total stripping ratio for the deposit is up to 2.55 tons per ton. So we need to pay attention to the adjustment factors with a lower value, and we'll compare it as a second option. So now let's focus on the economic indicators. More rock mass means more cost for its removal and processing, which is $88 million more, which is 8%. However, there is also an increase in profit of $60 million, which is 7%, and increase in NPV of about $11 million, which is 3%. As a percentage, these costs are still higher. And considering the result of financial activity for a long period, we can't ignore the discounted income, but its increase is not significant. Now, let's compare the coefficient of 0.72 with an angle of 39 degrees to the coefficient of 0.68 with an angle of 42 degrees. The export of rock mass is only 2.3 million tons, and the values of the ore export indicators are the same. This means that the entire difference lies in the removal of overburden. This is a great result, and it means that we get a decrease in the stripping ratio for the entire field and the costs are optimized. In terms of economic indicators, the trend is clear. Less of a burden with the same value of ore will result in a reduction of total cost, leading to an increase in the main economic indicators such as profit and NPV. Overall, increasing the angle of inclination of the pit wall by 3 degrees leads to an optimization in terms of reducing the cost of overburden and opens up new prospects for considering optimal contours if necessary. However, it's worth noting that this result is applicable to small and not significantly deep pits. The more pits they are, the deeper they are, more significantly this indicator affects them. The only thing left to do is to design them correctly. So when it comes to the optimizing the pit wall slope, there is also a need for caution. On one hand, we want to minimize the cost, optimize pit parameters, and reduce the cost of finished products. On the other hand, we need to avoid irreparable losses that can be caused by wrong calculations or incomplete understanding of rock occurrence conditions. These losses can lead to the suspension of pit operations, freezing the entire pit, and even loss of the equipment and loss of the personnel. So safety should always be the top priority, and the margins of safety should be respected and never violated. There's a joke that suggests that the pit should collapse the day after equipment and personnel are removed to allow for the maximum possible angle of inclination of the pit wall. But of course, we don't want to bring our mind to such state. So what if tomorrow the price of finished product increase, giving new prospects for development of the field? The global trend shows that the prices are rising because the resources are being depleted, so we can predict that very accurately. Now, looking at our illustrative example of optimizing the resulting angle of inclination of pit wall, we can conclude that even a slight change in this indicator can have a significant impact on the volume of rock excavation. In our case, increasing the angle by 3 degrees allowed us to reduce cost by minimizing the excavation of overburden, which is 2.5 million tons less, and obtain the same volume of minerals. It also enabled us to extract more minerals and extend the life of the pit and the enterprise as a whole, an additional 3 million tons of ore. Most mining companies are commercial organizations, and of course, they aim to increase profits. That's why the optimization process must be carried out continuously for all possible parameters while adhering the logical conclusion to ensure the safety of life, safety of property, and profitability optimization. Okay, great. So we have some questions here. So I would like to include in this conversation our technical sales engineer, Eugen, and our business development, Vitaly. Guys, are you here?
Yeah, hi Anya.
Yeah.
Hi.
Hello, everyone.
Hi. So the first question is, how often should sustainability and optimization work be carried out?
Oh, okay, I got it. So, based on my experience, the sustainability work should be performed at minimum in three different cases. So, first of all, it's to get knowledge of the deposit before the started mining activities at the site. The second one is to clarify the physical and mechanical properties in underexplored areas. And the third one, in cases to um, of apparent instability to clarify data and decide on the future actions. So also, I would like to highlight that stability monitoring should be performed on a regular basis. This is like a signal about dangerous is coming. And the deeper is bit, the more relevant the issue is. And what about optimization? So the optimization is usually performed once in a year using the updated information. But um, if the updated information is significantly different from the data on which the optimization was based, the optimization should be revised as soon as possible.
And there were two pitfall stability calculations during our presentation. First, calculation for rocks, and second for overburden. Um, did you guys use the same calculation methods for them?
Um, no, we use different methods in this case. To calculate the stability factor of hard rock, we followed the Hope-Brown failure criterion. And for the sediments or for our burden, we use the Moore-Coulomb theory, which is more appropriate for unstable rocks. And we can choose which method to use with the rock list. The selected theory will determine the list of physical and mechanical properties to be specified.
Okay, thank you. And the next question is, do we have a solutions for dump stability?
Yeah, we superficially discussed this aspect during the webinar. So let's try to explain it in more detail. K-mine offers two tasks to calculate the damp slope stability. The first one, using the calculation method with the foundation uplift in the calculate pit wall stability task, and the second, using the finite element method, FEM. The difference is in calculation method. It's a 2 or 3D mode and result output method.
Okay, thank you. And what to do if, after considering the pit wall angles, the design of the optimal pin contour has become wider and encroaches it on some expensive building, for example? What to do in this case?
Okay, so in this case, it is necessary to use the comprehensive approach to define the solution. You need to consider as many factors as it possible, all expenses and profits. So first of all, it's necessary to understand why the contours have been increased. So if it is related to additional profits, then the planning has to be done by moving the communications and to the new position and taking into account all expenses and comparing the NPV, for example, in both cases. So then evaluate the results and decide whether this activity is worthwhile. In the in case if the extension is related to global stability, or if it review on resulting angles indicates that the pit wall may become unstable, then there is no any questions of making additional profits. So the pit wall must be kept stable wherever the price will be. Additional actions must be done to stabilize the part of the open pit until the rock must become safe. So the relocation of constructions that exert additional pressure on the pit wall may be necessary. So each case is unique, and the solution depends on the skills staff that we could be involved on this.
Okay, great. And we also have a question of geological variability. Eugene, I think this question is for you, or maybe for Vitaly. How do we account for that in the stability analysis?
I think this variability we can use using a block model and information from a block model, and from a solid models, like a polygons on a sections that we will set the correspondence between the rock list, as I said before, and the polygons in a section if we're talking about the final elements method.
Okay, got it. Vitaly, do you have anything to add?
Okay, I can add only in case if you will use the block model, we just should to provide all necessary information inside of this block model. What we got input, the same will be the output.
Got it. Well, thank you so much, guys, for answering the questions, Eugene and Vitaly. Thank you so much, everyone who attended our webinar. Please don't forget to follow our LinkedIn page, and see you next time.
Okay, goodbye.
Bye.
Thanks.
Bye.
Bye.